Hm? Oops. So, hello everybody. Welcome back to our monthly computer vision meetup. You are here at the Manege, that's the office space of Anyline. I'm CTO and co-founder of Anyline. Daniel is my name, and we from Anyline are organizing this meetup. Here's Michael. He's always helping me with the live streaming and also marketing and everything for the meetup. So also this meetup is live streamed, so probably all the other 30 registrants are now in front of the live stream, or not? Sure, yeah. Sure. So for the speakers, maybe try to speak a little bit in the mic so that the 20 people on the live stream watching can also hear everything. Or you can also watch it later, so because it's then on YouTube streamed. So as most of the times, drinks are sponsored from Anyline, so feel free to grab a drink and cheers. And also, as most of the times, we are always looking for new speakers. So I'm glad that I found 2 awesome speakers this time, but it's always very hard to find good speakers. So if you want to share something, it can also be lightning talks, 10 minutes or 1 hour long master thesis or PhD stuff, whatever. I think we have 1 candidate over there for the next time. So if you have an idea, please talk to me, write to Michael, write to anybody at Anyline, and we can get you up here on stage. So that's it, basically from the organizational point. Today's agenda, we have 1 very interesting talk about if the Singularity is already near by Markus Oppitz over here. He's also my mentor and coach. And afterwards, we have baseline detection in historical documents using convolutional U-nets from Michael Sprinzel in the back. Maybe also there are the 30 people missing because you already spoiled your whole presentation on Meetup. Probably, yeah. No, I don't think that's the case. Yeah, so that's it. I think we just dive into the first talk and give a warm welcome applause to Markus.
Wait, 1 second.
Go. Okay, thank you, Daniel. Hello, everybody from my side as well. Markus Oppitz is my name, and Daniel already mentioned that I have the pleasure to coach him in building a great startup with Anyline, and I'm convinced he is doing a very good job. Okay? Andreas Greil-Huber is sitting next to him, and he had the crazy idea to invite me for a talk today, or in one of the computer vision meetings. I've nothing to
I will try to give you a brief overview of what's going on at the moment and what could be the case in the next 10, 20, 50 or 100 years in 30 minutes. I will try to do it in 30 minutes. Maybe it will be 31 or 32. I don't know. Okay? Everybody ready? So let's start with the 1950s. Because the word singularity is, or the term singularity is rather old. So the first reference I found is from 1958 from two real celebrities in computer science. This is Stanislav Ulam and John von Neumann. Everybody knows him, the von Neumann architecture. And they said, first, the accelerating progress of technology and changes in the mode of human life gives the appearance of approaching some essential singularity in the history of the human race, beyond which human affairs, as we know them, could not continue. And this is exactly the definition of technological singularity, a point in time where everything changes, and everything means not only technology, but also economy and everything we know today as mankind or human society. So why could that happen? If you don't know what's going on, what are you doing? Ask Gartner. So this is the Gartner Hype Circle of Emerging Technologies 2017, and who knows this Gartner Hype Curve already?
We are Gartner cool vendors.
Yeah. Anyline is Gartner cool vendors. So you know exactly what a Gartner Hype Curve is. The idea of the Gartner Hype Curve is that they publish that each and every year, and those little points here are different types of technologies. So you see, for example, here, digital twin, smart workspace, augmented data discovery, and what they are doing is they're giving to those little tiny points different colors, and the colors say this will come to a plateau of productivity, which is here, within the next 2 to 5 years, 5 to 10 years, or more than 10 years. So this is the basic idea of that Gartner Hype Curve. And if you take that technologies, and this is exactly the same list of technologies, ordered in a kind of universe. So you have in the yellow space here those technologies where Gartner says this will come to a plateau of productivity so that we can use it within the next 2 to 5 years. In the orange area, it will be something between 5 and 10 years, and the red one, this is longer than 10 years. And of course, the question, and this is also a possible explanation of what singularity is what will be here in that black point? Could that lead to singularity, to a point in time where everything changes, not only in technology, but also in economy and society? There is another interesting statistic, was carried together by Mr. Vincent Müller and Nick Ostrom, and what they did, they analyzed different predictions in papers of clever people during the last 20 or 30 years, and analyzed those predictions in terms of when will the strong AI, artificial intelligence case, really be available. And this is the result. So if you look at that, and it's very interesting to see there are some very optimistic predictions saying it will be somewhere around 2030. Then you have a group on not so optimistic predictions telling us it will be in 20 to 30 years or around 2050. And then we have a small group of people saying, no way, it will be maybe somewhere end of the century. So the question, when will strong AI come, is not easy to answer. If you ask 50 experts, and this is a selection of 50 experts, you will come out with 50 different answers. There are some very interesting statements since 1958, when John von Neumann and Stanislav Ulam talked the first time about singularity. So, for example, in 1965, Irving John Good was talking about an intelligent explosion. So what he said was, an ultra-intelligent machine could design even better machines. This is the idea that a machine could design machines. There would then, unquestionable, be an intelligence explosion, and the intelligence of man would be left far behind. And the same Irvin John Good said, this is the last invention of mankind. If that happens, it's really a singularity. There's nothing behind that that is comparable with human society as we experience it today. In 1993, Werner Winch said, this is the end of the human era. So if that happens, if that new superintelligence would continue to upgrade itself and would advance technology at an incomprehensible rate. Again, the idea of the point of no return, or as the physics would say, the event horizon. There's a very interesting book by Mr. Eden, Mr. Moore, and Mr. Soroka and Eric Steinhardt, an unfathomable change to civilization, which means if that happens, the invention of artificial superintelligence, this will abruptly trigger runaway technological growth, like that, resulting in unfathomable changes to human civilization. In 2015, Stephen Hawking said, maybe you have heard that, this is really something where we will be in trouble. And Stephen Hawking knows a lot about singularities, not technological singularities, but the Big Bang and the black holes and the event horizon. Elon Musk, last year, said AI is a fundamental risk to the existence of human civilization. And last but not least, you know that guy, and what he was saying last year, this is really something that should us think. Okay? So, 4 facts. So I was promising we would talk about facts, and we would try to talk about predictions and some scenarios. And I have 4 facts which are, I think, very important for the background idea behind what is happening in that way to a possible singularity, technological singularity. So the first fact is growth. And growth, this is very interesting, is the major principle behind human development for something around 100,000 years. It starts at the point where people invented agriculture and started to own something. And from that point of time, the only strategy to survive was to grow. And today, this is in our DNA. Nobody can think about a society or an economy which is existing without growth. And this is exactly what you can see, for example, at that curve. So these are the last 2,000 years, 2 different sets of data. One is the GDP, gross domestic product, was estimated, so real analysis of GDP started with the beginning of the 20th century, but there are some very good estimations. And the other one, the gray one, is the population, the world population. And you see, that looks like a hockey stick. Something happened 200 years ago, and those 2 different curves are referenced to each other. So the GDP, the production, is, as you can see, strongly related to population, because population is the workforce. As more people are working, you will create and generate more output. And if you generate more output, you need more people to work. So this is something that sticks together. And the second thing is that, of course, economic growth is also triggered by, or powered by innovation. What we see here is the same type of curves the last 250 years. Again, the gray one is population, the orange one is gross domestic product, and then we have some lines like websites, internet users, things like that. And you see that is really something where you can see strange things happen during the last 250 years, but also in the last 50 years. AI. Vista, one of those international analysts, analyzing markets. And what they say is that AI revenue, market revenue, will grow to approximately $60 billion within the next 7 to 8 years. This is a lot. Fact 2 is, as mankind, as human species, we are very successful. As you have seen, a lot of growth in population and also in GDP. And the question is, what will be the future of the human population, and what will be the future of GDP within the next 50 years, 100 years, or 200 years? And the message here is population is still growing, but as we have learned during the last 10 or 20 years, not endlessly. Why? Because the total fertility rate, birth per woman, is shrinking. And that, of course, has an influence on the population growth rate. The population growth rate was around 2% between 1950 and 1990. And then it started to sink. And today we have a population growth rate of 1.1, and projections coming from the United Nations and the World Bank are telling us it will go down to 0.1% by end of this century. And this is dramatic, because it has, of course, a major influence on how many people are we on planet Earth. And if you look at that, world population by age, you see it's still growing, starting with 1950. It will grow for the next, let's say, 30 to 50 years. But that growth will stop maybe by end of the century. And that, again, has a major influence on a very important parameter when we're talking about growth. It has a major influence on the workforce. And this is the percentage of people between 1950 and 2100 who are members of the workforce, people in the age between, let's say, 18 and 65, compared to children and to people that are older than 65, retired. And as you can see, at the moment, we have a workforce of 56%. It was growing from 1950 because there was a baby boom, for example. And now it's shrinking. And by end of the century, we'll have a workforce part of only 52%, which is dramatic, because these are people who cannot contribute to the GDP, to the production, and this will have a major influence on economic growth. So maybe the idea of growth, which is in our DNA since 50,000 or 1,000 years, has to be changed. Fact 3 is paradigm changes. So a paradigm change is something where really important things change, and there you have a very interesting list that was put together by Ray Kurzweil, and there's a web page with all that data. And this list is a list of approximately 300 major paradigm changes in the last 100,000 years, like, for example, usage of fire, the first application of agriculture, writing, printing, steam, and then, of course, electricity, telegraph, digital computers, wireless communication, all that kind of stuff. And if you look at that, and be careful, both axes are logarithmic plotting. Yeah, so this is not a linear thing, because if you would print that as linear curves, you would see nothing. The message behind that is that for the last 100,000 years, the time to next event was shrinking. So paradigm changes are coming in shorter distances. So between fire and agriculture was something like 50,000 years. Between agriculture and the first writing was something like 40,000 or 35,000 years. between the invention of printing and electronics or digital computer, it was 550 years. And if you look at that in a more detailed graphic showing major paradigm changes between 1750 and 2100, so the last 250 years, you will see there was steam, there was railway, telegraph, electricity, and there's a lot of time between steam and railway, railway and telegraph, telegraph, electricity, and then you came to our time. And if you think about what had been the major paradigm changes in our time in technology and IT, it was of course a digital computer, but it was of course something like software is reusable, something like access to information is free or data is value and currency. And if you plot that, you see there's a huge group of paradigm changes that happened in the last bandwidth using different technologies is growing exponentially with a factor of around 50% per year. This is exactly Nielsen's law. Mr. Nielsen is calculating that since, I don't know, 20 or 30 years, and that Nielsen law is still applicable, which means if you have a growth rate of 50% per year, then it will grow by the factor of 60 in 10 years, bandwidth available to each of us, and it will grow by the factor of 3,300, 3300, in 20 years, which is quite a lot. Think about 3G, 4G, 5G, and so on. The same happens with processor capacity. These are typical processors based on old ones, mechanical or tubes, silicon, projections for 3D molecular processing, DNA computing, and those blue one here are estimations for quantum computing. And they have the same effect. It's again a logarithmic plotting showing us that we have a growth rate of 60% per year, which means factor 100 in processing capacity within 10 years and 12,000 within 20 years. And if you compare that now with the theoretical capacity of the human brain, then you will see that within the next 10 to 20 years, we would be able to model the human brain, at least in terms of capacity, with a computer. There are different estimations what capacity the human brain really needs. It's something between 10 power 18 and 25. But if that curve is really true, then it's a question of maybe 10 years. And this, of course, is a very important signal that something like artificial intelligence, strong artificial intelligence, can happen. The same is the case with cost of processing. So if you look at that, this is sinking. Again, this is logarithmic plotting. And that leaves us, of course, with the question, what about the humans? What about us? Are we able to manage that? And the basic message is that today, many people have the feeling that they are overtaken by technology. This is a statistic coming from United Nations, the United Nations Development Program. What they are doing, they are trying to estimate the Human Development Index, which consists of three major dimensions, as they call that: life expectancy, education, and the gross national income. And they pull that together and report what is the Human Development Index in different countries and different regions. They are doing that since 1990, and these are the different curves for different regions of the world. And as you can see, this is nothing that has the same exponential growth as we experience with technology, which leads us to this diagram, simply showing there is a human development, we are developing, we are learning more, we gather more experience, but not with the same speed as technology. And this, of course, is the problem. Many people today have the feeling that technology is overtaking their capacity to survive, and maybe this situation will be worse within the next 5 or 10 years. So, maybe artificial intelligence is the way out. What do you think? Let's try to find out. So, first question, what is intelligence? Not easy, nobody knows that. So what we know today is that it seems to be a combination between the human body and the human brain. And because we are information scientists or IT specialists, the human body is something like the hardware consisting of cell, tissues, organs for different systems. So this is a system structure of the human body. It's consisting of systems for circulation, for digestion, nerves, muscles, immunization, reproduction, and so on. On the other side, the software, or something like the software, is the human brain. This is much more complex. Nobody really understands today how the human brain works. There are parts we understand rather well, but we are far away from a complete understanding of the human brain. So what we know, for example, it's an architecture consisting of synapses, neurons. They form a highly coupled network. It's slow, but is massively parallel. It is a combination of analog and digital processing, and it's a combination of chemical and electrical processes, which is, of course, very different from a computer. Has nothing to do with a computer. So we have two problems. We don't understand the complete functionality of the human brain, and one thing we know, it's not working like a computer from its architecture and from the structure of the so-called software behind it. So if we say intelligence is something like a combination between body and brain, then we have applications in the middle, what we would call applications. And this is a maybe not complete list of applications. Intelligence consists of senses, language, cognition, understanding, reasoning, learning, emotion, self-awareness, very important. It consists of subconscious mind, the Unterbewusstsein, where in Vienna, Mr. Freud was the one who analyzed that for the first time. It has a very important application which is called fictional language. We can talk about things which are not real. We can tell stories, we can build legends, like religion, for example. You will see that a little bit later. Consisting of fantasy, dreams, creativity, we can innovate, we are very innovative. We are very good in cooperation. We have something like ethics. Everybody has a different one, but there is something existing like that, and it's part of intelligence. And we have something like a free will, which can be discussed, I know that, but it's existing. Maybe again as a fictional term in our language. What we don't have endurance, we are getting tired. We don't have immortality, we are mortal, body and brain. And we are not really good scalable. Yeah? So this is maybe not a definition, but a description of what intelligence could be. And now, of course, we have to make the next step. What is artificial intelligence? And this is my try of finding a definition. And of course, we have to compare artificial intelligence with biological human intelligence, and we have to differentiate between a cognitive machine and, on the other side, strong artificial intelligence. And this is my definition. So if we say there is something like a cognitive machine, a smart system, or as some people say, it's weak artificial intelligence, it has a lot. Yeah, it had senses, language, cognition, understanding, reason, learning. This is a definition of cognitive systems. but it does not have emotion, self-awareness, subconsciousness, fictional language, fantasy, dreams, all these things that are very important for our understanding of intelligence. But of course, it may have endurance. It's maybe immortal, it's well designed, and it's highly scalable. So this is the first definition of what is a cognitive machine. Artificial general intelligence is something completely different. So there it's very clear that the definition has to be, this is the intelligence of the machine that could successfully perform any intellectual task that a human being can, which means it has to have emotion, self-awareness, so all those applications or attributes we understand as intelligent. And last but least, what is a super artificial intelligence or a super intelligence, which could lead to the singularity in the end? This is any intellect that greatly exceeds the cognitive performance of human beings in all domains of interest, which simply means it's the same, but it has here huge scalability. It could be, as briefly said, as smart as the complete population of planet Earth, and smarter than that. Okay? Does that help? Depends on what we expect from life. What is the meaning of life? Beliefs are very important. What we believe is very important for how we feel about our existence. The typical philosophical question is, where do we come from? Where will we go to? And what the heck are we doing here? And to answer that question, you need some kind of belief. You have to believe in something. In a legend, in a story, in a mysticism, anyway. And those beliefs are triggers of social change. And you can see that for more than, again, 100,000 years, the major belief of the Homo sapiens was into any type of God, and we call that religion. And it was not longer than 400 years ago that Mr. Newton analyzed why an apple is falling down, and his conclusion was, it's not God, it's gravity. And that was the invention of the scientific revolution. And from that point of time, there was another type of belief. Those people believed maybe also in God, but they also believed in gravity or in natural laws. In the 18th century, human rights appeared. So somebody decided to write down, started in America and then in France, a list of things which were interpreted as human rights. This is nothing like a natural law, and it's nothing you can prove. It's something we believe in. Who is believing in human rights in that room? Okay, should be everybody. Who is believing in natural laws? Gravity, things like that? Okay, everybody. So, who is believing in free will and self-determination? Yeah? Is there a proof for that? There's no proof for that. But we believe it. We believe it because we think it's good to believe it, and we are feeling fine if we are believing in free will, self-determination, human rights, and natural laws. And this is very important. And this is also something that could be changed by a singularity. So the question is, what will be the next step? What will we believe in 30, 40, or 50 years, or 100 years? This is a very nice statement from famous Mr. Linus Torvalds. He said there are 3 things that have meaning for life. And they are the motivational factors for everything. The first is survival, the second is social order, and the third is entertainment. Which is maybe true. So there's a lot of business in entertainment in those days. So the question is, and it's a philosophical question, where are we today, and where do we want to go within the next 100 years? And if we look at the left side of that equation, then this is a list of things we achieved in the last, let's say, 100, 200, maybe 300 years. First of all, it's no question we're the most successful species in the world. Huh? Any doubt? No, we are. And as we have seen, we believe in humanism, we believe in self-determination, we believe in free will. Everybody in this room does that. Maybe not everybody on the planet, but a lot of people believe in that. We successfully fight hunger and disease. That's true. If you look at the statistics, it's still not good, but it's much more better than it was 100 or 200 years ago. We stopped population explosion. We have seen that as a statistic. We are on the way to stop it. War is no longer a major threat compared to 100, 200, 300 years ago in terms of how many people are killed in wars. Those numbers are much more lower than they have been in the 18th, 19th, and 20th century. Life expectancy is high, going up to 80 years, we know that, compared to 40 years, 100 years ago. Technology performance is growing exponentially, we have seen that. Our innovation capacity is high. Yeah? We could fight climate change and pollution. We are not very successful in that domain at the moment, but we are convinced that we could do that. And we could manage the planet's natural resources. So there are a lot of things which had been really problems for survival and for our social position 100 and 200 years ago. And they are solved, or nearly solved. So the question is, what's next? And Mr. Yuval Noah Harari, thank you, Daniel, he told me about that book. He's saying in his book, Homo Deus, A Brief History of Tomorrow, that's easy. Our next goals are immortality, happiness, fun, entertainment. This is what Linus Torvalds is saying as well. And maybe divinity, you want to be like gods. Maybe that could happen. Because we have solved so many problems, why not that? So we have 5 scenarios, where and how to go there. And some of them could lead to singularity. Scenario number 1 is the techno-humanism. This is an easy one. This is exactly what happens today. We are in the situation, we will always have those structured slides for each of those 5 scenarios. At the moment, we are in the situation that we believe in human rights, natural laws, self-determination, and free will. So we are able to vote, and we are obeying the human rights, or at least most of us are doing that. What techno-humanism is promising is everything could be much more easier if you would accept those great new technologies. It would be much more efficient, much more comfortable for you to drive a car. You don't have to do that in the future. You will gain perspective using that great Google Glasses or whatever. You would be much more healthier using that smartwatch and wearables. You will have a lot more fun, of course. And you will get smart help from those nice little smart robots. Nothing else will change. You will still have your human rights, you can still believe in natural laws, self-determination and free will. It's another type of humanism. It's not humanism, it's techno-humanism. Sounds good, can happen. So, what do we need? What are the prerequisites? We need user acceptance, we have that. Everybody, many people are accepting today the Googles and the Facebooks and the wearables and the new gaming stuff. So that's not really a problem, and we need successful business models, and we have them. A lot of companies are around us who are really making great money doing that. And on the shopping list are some cognitive things, so it would be nice to have cognitive expert advisors, cognitive systems, smart robots for home, for example. It would be nice to have connected homes, smart workplaces, conversational user interfaces, so some of those emerging technologies Gartner is talking about. but they are in the area of, they will be here between 2 and 5 years, maybe 5 to 10 years. So that will happen. And the question is, and I have tried to create a SWOT analysis for each of those scenarios. So techno-humanism, what are the strengths, the weaknesses, the opportunities, and the threats? And I have decided to put into the first line, strengths and weaknesses, the perception for the individual. So what does that mean for me? I know.
I think it's very interesting.
Yeah. And in the second line, it's the external perspective, which means what does that mean for society, for mankind? Because these are the two things that should be interesting for us in looking at scenarios and maybe singularities that could appear there. So the strengths are easy: efficient, comfortable, great perspective, health, fun, smart help. I like that. What are the weaknesses? Okay, dependencies on companies, monopolies, lifelong learning. Yeah, okay, I have to change. I have to learn the rest of my life. Fine, I can stand that. Opportunities are a lot: new business, new jobs, fair distribution of goods, much more efficient production, and it would maybe include a solution for the workforce problem, because we can use robots to expand our workforce. Would be great. There are some threats: data privacy, cybercrime, job killers, but we're used to that. We could handle that. So this is a very smooth way, and I think this is already happening. And it's not something that will end in a singularity. It's a evolvement. The second thing is a little bit more dangerous, and it's called dataism. And dataism is following the idea that a biological algorithm, me, or maybe also my dog, is the same like a digital algorithm. Both are algorithms and are acting on what they call a data stream. So I can build digital algorithms working on a data stream, as well as we are working on data streams in terms of the data we receive through our senses from the environment. And the idea of dataism is, if the biological algorithms and the digital algorithms share the same data stream, that would be great for the biological algorithms, because they could receive a lot of help from the digital algorithms. They could tell me when to stand up in the morning, they could tell me what's the best, I don't know, job I could take. They could tell me with which persons I should connect, because maybe one of them could develop to a friend or to my future wife. They could tell me when to practice, they could tell me when to learn, and these are all things that already happen. Yeah, you know that. Your social media networks are telling you a lot about yourself, and there was a statistic 2 or 3 weeks ago in the media that said Facebook could tell you more about you than yourself if you have something like more than 50 likes on your postings. Yeah? And if it's more than 150 likes, Facebook could tell you more about yourself than your father or mother. Yeah? So we are still in that stream, that a global data stream, let's call it that, together with digital algorithms, can tell us more about ourselves than our friends could do or we can do. And this is maybe something that will really happen. What do we need for that? User acceptance, we have that. Successful business models, we have that. We need a little bit more. We need a global industry that has to be organized, but it can be done. And we need a global network of things, pulling together all that data. Shopping list is the same. Cognitive expert advisors would be nice. Deep learning, machine learning would be nice. Would make that digital algorithms much more smarter. Cognitive computing would be nice, and we would have things like virtual twins or virtual assistants, all things where Gartner says this will come not within the next 10 years, but maybe after that. But it's not too far away. It's already on the curve. The outcome will be no free will, because the global data stream will tell you everything. You don't have to make any decisions. The outcome will be you don't have to believe in human rights, because the data stream will tell you what to do. There's no need to believe in natural laws, because the laws are in the algorithms, in the global data stream. So the situation will change from humanism and liberalism to what is called dataism, which is not, which makes you maybe a little bit nervous. And if you look at that SWOT analysis, there are a lot of strengths. One of the strengths is less decisions for the individual. I don't have to make decisions anymore, because those digital algorithms and the data stream will do that for me. But of course, on the other side, we have a lot of dependencies. We have limited self-determination, limited free will, and the major threat is this is the end of liberalism. So if you believe in liberalism, forget it. In that world, you have to believe in global data stream. Who wants to believe in the global data stream? Hands up. Nobody. Okay. So now, superintelligence. Scenario number 3. So the question is, how can we achieve that? And as far as I understand it, there is one major plan that could work. No guarantee for that. But that plan says what we have to do is we have to copy a human brain, or maybe many human brains, using nanotube electronics and a brain-computer interface, where again we know this will come within the next something like 20 years. We will have to paste that copy into a new hardware, which could be a neuromorphic hardware. It could be available on a productive plateau within the next 30 years. We have to connect it to the data stream to give experience to it, because experience is very important. And then we can scale it using, for example, quantum computing. Scaling means performance across 10, 100,000, 10,000, whatever. And the result will be the superintelligence, no question, could be. Perspective is, or prerequisite is, we need somebody who will pay that. We need somebody who has a reason to act. Could be Mr. Putin, but Mr. Putin doesn't have the money, I think. But could be somebody in US, China, who knows. And this one should have no ethical doubts, because this is really something dramatic. Shopping list is short. All we need is nanotube electronics, brain-computer interface, neuromorphic hardware, quantum computing. If we have that, we could follow that plan, theoretically. But of course, if you look at that SWOT analysis, this is terrible. So there are no opportunities for society or mankind, because if there is a superintelligence, what will happen? Either a single political power could take over, but you have to take into consideration that a superintelligence, which is as intelligent and powerful and quick as, I don't know, the complete population of planet Earth, we could not lock that one in. You cannot control it. So the theory behind that is, and that comes from another celebrity in Singularity thinking, says this superintelligence could take over power within minutes or maybe seconds. At the moment, you have loaded that copy of those human brains into a powerful architecture connected to the data stream. It will take over power. No chance to control that. Which, of course, means no more opportunities for society of mankind, or mankind. There's maybe one strength. You don't have to make any decisions anymore, because there's Mr. Superintelligence, and he will tell you what to do. Weakness is clear. End of the primate of Homo sapiens, end of self-determination, end of free will, end of humanism, end of liberalism. This is singularity.
We can hope that it figures out that all we need is entertainment and give us entertainment.
Could be the case. Maybe this is an opportunity. Okay. So, biological optimization. This is another scenario. So, this is about we could manipulate our DNA, yeah, optimize, augment it, or augment the human body and brain. And this is a scenario that could happen. What do we need? We need again funding, reason to act, and no ethical doubts, and we need technology for genetic manipulation, and we need technology for human augmentation to improve the body, but also to improve the brain, and also improve our DNA. And there are already technologies out there who are exactly doing that, so that could happen. So what's the effect? The effect is you will have a two-class society. One class will consist of those people who can afford that, or can pay that for their children, and the other group in society will be those who cannot afford that. This will be the slaves. So if you look at the SWOT analysis, there are a lot of strengths. Again, it's very efficient, comfortable. You will have a lot of perspective, health, fun, happiness, personal power. If you are upgraded, your body, your brain, and maybe you will be immortal. So this could fulfill the question for immortality, because if upgrading is successful, you could live forever. Weakness is immortality again, because who wants to live forever? This is maybe not really funny. And of course, there are no opportunities for society and mankind. Nothing positive I would think about, I could mention. And of course, it will be a two-class society. It will be again end of liberalism and end of humanism. Last but not least, if we don't like that, we could move ourselves in the cyberspace. So again, this is something that could be done. We need user acceptance, we need again funding and business model, but the shopping list is the same. We need something like nanotube electronics to scan the brain. We need neuromorphic hardware, brain-computer interface, and quantum computing, and then we could copy ourselves into a machine and live a virtual existence. There are many people who are doing that today, sitting in front of the screen, and I know all they think is I would like to be on the other side, because I don't like my body here, and all the junk food. It would be much more fun to be on the other side of the computer screen. We think in that sometimes. Come on. Good. Are there any hackers here? Are there any hackers here? No? What type of community is that? No hackers? Okay. Hackers would say, yes, I would like to have a virtual existence. It's much more fun. So, a lot of strengths. Again, efficiency, comfort, perspective in the matrix. Personal power, you would be immortal again. But of course, it's again a two-class society. Those who will be copied because they can afford it in cyberspace, and the rest of Homo sapiens will be left over as, I don't know, somebody who is, I don't know, maybe working, maybe not. Nobody knows that. So, now it's your choice. What do you guess? Or what will be your preferred way? You should think about that. But you could also do some readings. This is a very short list of recommended readings. I mentioned Hariri. This is really a very fascinating book. I also mentioned Nick Bostrom, about superintelligence. I mentioned Ray Kurzweil. I think he's the most famous myself to mention myself because I've written a book together with Peter Thompson about inventing the cloud century. There are some chapters about cloud digitalization and paradigm changes. And if you want to read something and having fun, there are 4 books which have to do with paradigm changes and singularity, which I really recommend. This is Linus Torvalds Just for Fun. Very funny book. And there's a Austrian Viennese author, Mr. Mark Ellsberg. Who has heard about Mark Ellsberg? Okay. And he has written 3 books, and all of them are about some type of singularity. And all of them are thrillers. Very, very fascinating to read. What I like with Mark Ellsberg, he is really somebody who did a lot of research. And he is invited, for example, by organizations like the Deutsche Bundeswehr to give them consulting about problem situations. So he's really a smart guy, and reading those books is really fun. Okay, so questions. Are you shocked, or are you falling asleep?
If you're talking about the superintelligence that's so dangerous, what's the motivation of the superintelligence to become dangerous at all, to do anything at all?
Yeah,
Does it realize it has no motivation to
yeah,
evolve, right?
yeah. If it's a intelligence, if it's a superintelligence, it has to have goals. Yeah? And to be honest, nobody knows today what type of goals that could be. So one model is again that HAL computer in 2001 Space Odyssey, which had a goal to complete the mission. And one result of this algorithm was to kill the people on board. Yeah, because they were a blocker for the completion of the mission. As you remember, maybe who has seen that movie? Very okay. Exactly. And this is a good example. You never know what is the goal of that superintelligence, because you cannot give the superintelligence a goal, because in the same moment the superintelligence will change that goal, optimize it. And within minutes, the superintelligence could have other goals.
Exactly.
And one part of the strategy could be, my goal is to rule the universe. And the first step is kill the population of planet Earth, because they would hinder me. You never know.
It's not all that bad to rule the universe from my point of view. It's just the major goal is to survive for the superintelligence. The only one who could destroy him, or she, whoever she, him,
Yeah.
it will be, are we.
Why does it not survive? What's the point?
If you have
If you have self-consciousness, yeah, then
self-consciousness, feeling for life, then you want to survive.
yeah, I think this is
our point of view, yes. But I mean, if I'm going into atheism, and if you go there, then what's the point of living? So if you have a superintelligence, I mean,
maybe the superintelligence is the goal to have fun. And to have fun, it has to survive.
maybe
And if humankind, or the people, humans, are hindering that, because superintelligence needs, for example, the superintelligence decides, I need all the resources of planet Earth. Yeah? All natural resources. And those innocents crawling on the planet's face, they are hindering me. So to achieve my goal, I have to eliminate them.
You said before that you don't know the goals for the superintelligence, but you either don't know the goals of other humans.
True. This is a question of belief. I believe that other humans have goals, but maybe this is a complete misunderstanding.
Yeah, but you don't know the goals from the humans, because
take away emotion from what we experience as intelligence, then it would not be the same.
It wouldn't have any goals.
But then it's not intelligence. This is what I think. Yeah, I think if we define intelligence as that what we are or what we believe that we are, then emotion has a very strong relationship to innovation, creativity, subconsciousness, dreaming, fantasy. I cannot imagine about fantasy or creativity without emotion. Maybe it's existing, but I think it's part of our intelligence. That could be a super intelligence which is not super intelligent, but super cognitive. Yeah. So if you say it has cognition, it's able to reason, to understand, but it has no emotion, then this is maybe a smart robot, which is very powerful in helping us, but it's not a super intelligence. It's a super cognitive machine, which is maybe nice because it would be helpful. I think this is exactly the difference between cognitive machines and intelligent. Okay?
Thank you.
Asimov had also a great take on how a superintelligence turns against us. The 3 rules of Asimov.
The robotics,
Romance, don't harm a human and don't harm yourself except to harm a human. But he involves then the rules to capture all the humans because he has to save them from themselves because humans that's also how they could take over and evolve their goals. So maybe we make a 5-minute restroom break and refill break, and then we start with the second talk. Thank you. Was habe ich da nicht aus, ja? Ich sag nichts mehr dazu. Ist das jetzt leider. Mit dem wir das.
Tim. Ja, dann nicht. Ich wollte eigentlich nur meinen Presenter anstecken. Oder geht das mit dem Mac nicht, gell? Jawohl? Okay. Okay, er wollte nämlich dann. So, er wollte nämlich dann nur.
Wo kommen wir presenter?
Also, okay. Ja, ich habe nämlich keine Shift-Taste. Okay.
Ja, der Mund, das ist ein Keyboard, was du
Ja.
da hängst.
Ist kein Problem, sonst mache ich das mit dem. Ich wollte eigentlich nur zum Hin- und Her schalten. Warte mal, ich probiere mal. Ja, geht eh. Sehr gut. Perfekt. Besser. Super, danke. Mit der Mac-Umgebung nicht so ganz. Wie du magst, oder?
Ja, so, I think we can continue. Okay, we wait for 2 more minutes.
Yeah, okay. Welcome everybody to the second talk of today's Computer Vision Meetup. what I'm going to talk about is baseline detection in historical documents using convolutional units. This is a paper that we recently published at the document analysis system workshop that took place in Vienna in the end of April. Before I uploaded the slides of this talk and the paper, in case you're interested, I put the links in the meetup comments, so in case you're interested in, you can download it from there. I would like to start with an introduction of myself and also about the company I'm working for. I am Michael Sprinzel and I'm working for a company which is called Deutsches Medizinrechenzentrum. It's a German company, as you might have already concluded by the name. And our headquarters is in Düsseldorf. It was founded 2007 by Georg Mackenbrock and two other partners. And at the moment we have about 50 people working in Düsseldorf. In 2016 they founded an office also in Vienna, where I'm working at the moment together with my colleagues Michael Fink and Thomas Leier. So I mentioned that it's about baseline detection, so I don't assume anyone or all of the audience to be familiar with what a baseline is, or does all of you know what a baseline is? Okay, then I've prepared a quick slide. So what is a baseline? It has to do with OCR and typography. So like I've chosen a handwriting example, so when you write the word like hello, then we can define 5 lines when we're talking about typography. The most important one is the so-called baseline. In this case, the baseline would be here. That's the line on which the letters rest, or at least, if not all of them, at least the majority of them. A second quite important one is the so-called X height. That's the height of the lowercase characters that are neither ascenders or descenders. So you can see the descenders are going down until here. These are characters like P, Q, and J, while the ascenders move up to the ascender line here. These are the letters like B, D, F, and so on. Sometimes there is also a cap height which defines the height where the capital letters go up to, but this is not that important. So for the rest of for my talk, it's sufficient if you remember what a baseline is. So now we know what a baseline is, so why it is so important to find a baseline, because it's a very crucial step as a pre-processing step when we want to perform handwritten text recognition. Text recognition is already, handwritten text recognition is already difficult when we are dealing with up-to-date documents, but it gets even more tricky when we are dealing with historical documents, because they have a quite complex structure, and due to the long storage, they also show a high amount of degradation. So they are faint typing, bleed through, holes, ornaments, annotations, all kind of that stuff. Handwriting text recognition is an active research topic, so there are regular competitions on that. So there was a major conference on handwriting, the so-called ICTA conference, which took place in Japan in November last year, and there was a competition there, the so-called CBAT competition, and we were quite proud to that we are the winner of this competition. And what I'm going to present today is the system that we used for winning this competition. When you look at the literature, all systems, or the majority of the systems up to now is using machine learning based systems to find a baseline. But they are using LSTM, so long short-term memory networks. We also tried that, but we were not 100% happy with the results, so we played a little bit around and we found another architecture quite useful for that. We are proposing a so-called unit architecture, and we use this architecture together with the classical sliding window approach. So what I'm going to tell you in the next 15 to 20 minutes I would like to propose our system architecture, which mainly consists of out of 3 parts. So we have one part which we call the so-called DA-net, which does a very simple form of document analysis, because we definitely have to know where are the baselines within the document. Of course, then we have a second part which takes care about the baseline detection itself. And afterwards, we make some kind of post-processing, because we get a number of candidate lines proposed by the baseline nets, and we have to post-process them in some way. I already mentioned we were the proud winners of this CBAT competition, so I will present our results and also the results of the other teams that took part at this competition. And then I go a little bit more into the results and show which part of our system architecture contributed to the results that we achieved at the competition. We also wanted to make sure that we are not just trained our algorithm or to one specific data set. So what we also did, we took another data set and we also run our competition, our architecture on the second data set, and we were also able to outperform the contestants of the second competition. Yeah, that's for short the outline of the remaining 15 minutes. I will start with a slide that should describe our overall workflow with more or less one slide. Our input is an historical document, as you see here on the left-hand side. The upper part is the part that is dealing with the document analysis net, while the lower part is the net that is responsible for the baselines. As I mentioned, we're using a sliding window approach. I guess sliding window is a common term for people working with deep learning. So we use the sliding window approach, and the output of the DA net is a binary mask where the white pixels are denoting the foreground pixels, the black pixels are denoting the background pixels. So what we get here is just a prediction where we think that we can expect the baselines to be within this document. But we just get not even a binary mask, we get also some additional classification out of our document analysis net, which we also forward into the net which is responsible for the baselines. And these document properties we are using to calculate a dynamic scale factor, because for the DA net we're using a fixed scale, but for the BL net we are using a dynamic scale. I will show in a minute how we do that. So the BL net produces a number of candidate lines, and we afterwards doing some kind of post-processing, so we are cleaning spurious candidate lines, and we are trying to join these candidate lines into polyline baselines. So that's I'm try to show our workflow within one slide. So let's dig a little bit deeper into the architecture. As I mentioned, we are using, we are proposing a so-called UNet architecture. The UNet architecture has its name because it's the shape of the layout more or less is similar to the letter U. So you have on the left-hand side a contracting path, so where we on each layer have a number of convolution layers, then we have a max pool layer, and so on. So the contracting path is here on the left-hand side, then we have a bottom layer, and on the right-hand side we have an expanding path. But this would not be a very super new approach, but we also have on each level we have a direct connection from each contracting path to the expanding path. So we are already forwarding information directly from the beginning to the end. So this overcomes the most famous vanishing gradient problem, and also ensures that the precision that we're getting is really high. So for the guys dealing with CNN, I also wrote some specs of our net here, so you can also look it up in the paper within more detail. So as I just go quickly over it, we are just using sliding window of 160 by 160 with a stride of 40, so we get 16 predictions per pixel, and we are voting for this pixel as a foreground pixel if we get a maximum count of at least 0.5. And then we build a connected component, foreground metric out of it, and we blow up the mask by doing a vertical sampling. If you look very closely here, I hope you can see it's written here auxiliary layer at the bottom. So I mentioned we are also getting auxiliary layer, and we get 4 output of these auxiliary layers, and these auxiliary layers, we get 4 predictions for, namely a prediction if the leading is high. This means the vertical distance between 2 baselines. If the document we are dealing with is a double page document, or we just expect a single page on this document, if the document is vertical or landscape, or if there is any text at all at the document. Because there were also some documents within the test set that just contain graphics and no text at all. This was the net which is responsible for the document analysis. We also have a second net which is responsible for the baseline detection. Again, here are some specs of the net. And here we are using these 4 document properties that I showed on the slide before to calculate a dynamic scaling factor. This is our super world formula that we figured out. So we are supporting 7 different scales from 512 pixel up to 1280 pixel. And we are calculating this dynamic scale using this formula. So you can see the first term here is more or less an initial scale guess, and the scale guess can either be increased if the document is a double page document, or it's a landscape document, or it can be decreased if the leading is high. So for the baseline extractions, we again using a stride of 40, but we are just using an inner mask of 80 by 80 pixel out of this 320 by 320 pixels here, which gives us just 4 predictions per pixel, but this is more or less more than sufficient. And we then construct the polyline segments by a least square. So the BLNet is proposing a set of candidate lines. Of course, we have to do some post-processing. We do it in 2 steps. The first step is a so-called pruning. So we try to get rid of candidate lines that are either disoriented or they are covered completely by a longer baseline segment. And the second post-processing that we are applying is joining. So we try to join baseline segment that have a similar angular and a similar horizontal orientation. We do this in 2 passes. So the first pass we just allow non-overlapping joints to the right, while in the second pass we also allow overlapping joints to the left. That's so far to the post-processing. I already mentioned we were able to win the CVAT competition. So what was this about? It was a data set that was compiled from 9 different archives, so it was a very heterogeneous data set. There were 2 tracks, track A, which was called the simple track, and a track B that was more complex. The simple one just contained text without any distortions, while the track B included also rotated documents, documents with tables, with graphics, documents with no text at all, so any kind of distortions you might think of. And what you can see here is the results that we achieved together with the other groups. So the UP VLC is the University of Valencia, then there is also the BYU, which are the Brigham Young University in the States, so the Mormon University, and then also two French guys. Drawn here in red is the precision that our algorithm, or that the algorithms produce. Green is the recall, and the blue line is the so-called F value, which is just the arithmetic mean between the precision and the recall. Just go through the results. So you see we outperformed the other contestants in both tracks. The guys from Valencia were, with respect to the precision, quite close to us, but unfortunately the recall is much worse, so which gives the finals, which draws back their final score. From one of the French guys, they just committed to one track, and yeah, so in case you really want to take a more detailed look at the figures, you can have a close look in our paper. It's written once again there. So I already mentioned we want to have a more detailed look which part of our system architecture contributed to the results that we achieved. So what we started in the beginning we didn't invented this dynamic scaling. So we also used for the BL netted fixed scale. And you can see here the precision and the recall that we started with. So the precision was in both tracks about 76%, while the recall was of course much higher in the simple one. Then we came up with the idea to do the individual scaling, because the data set was very heterogeneous, and also the input images showed a very large variety within the width and the height. This already brought us forward about 5% for the simple track in the precision, and about 2% on the more complex track. But even more important was that we introduced this pruning stuff. So you see we improved by more than 10% here. Of course, we also lost a little bit of the recall because we also pruned some baselines that we shouldn't have pruned, but nevertheless we gained 10% here, so it's definitely worth doing this. And for the simple track, we also added then the joining, so we again increased a little bit on here. So that's the progress that we made from the beginning till the full-featured system in the end. I just mentioning here we did not apply the joining on the complex data set, because there are also a lot of documents in there which are tables or some kind of structured documents, and we were not able to find a reliable algorithm to detect the structure. So we would have joined over the border of the tables, and this was penalized by the evaluation algorithm of the competition. So many numbers and many figures so far. So let's see some nice pictures. So yeah, here you see an example where everything works very good. So we have a disoriented baseline here that we are pruning correctly, and we also have baselines here that we are joining correctly, and also here we make a so-called set join. So this is one of the joins that was done in the second part, so we allowed joins to the left. As I mentioned, pruning not always, the pruning also joins prunes lines that we shouldn't have pruned, like in this example, or like in this example, we are joining two baselines that should have stayed separated. Some other examples. So here you see the ground truth that was provided by the organizers, and here you see the mask that our document analysis net is providing. So it looks quite good. We also get this baseline in here, but we also get some false positives here because we also consider this as a part where we expect baselines, and there are baselines here, but in the ground truth they are not valid baselines. So nevertheless we get them, so we get some false positive results here. Another example which is not going so well, so you see we are missing some parts here on the upper right hand side, we are also missing a baseline here. But what you can see here, which is even more worse, is these baselines. This is a document which shows a table structure, and we are joining here the baselines over this table border. And this gives us very bad results because the voting algorithm that is calculating the precision and the recall penalizes this in a high manner if you join some stuff like after we won the competition, we were also interested how well our algorithm generalizes. So we tried our algorithm on another data set to see how well it performs. Luckily, there was a second data set at the same conference, the so-called HISTOC data set, and you can see here the results from the best contestants from the other competition, and we tried our trained network right away, and we got quite bad results. Why is this? Because there was a specialty of this HISTOC stuff, which you can see here. So how this was like the HISTOC documents look like. So you can see here the baselines which are defining the text, but I hope you can see there is also text written in between. So, and these are called interlineary glossaries. These are comments or corrections or additions that the author added afterwards, after he was writing the document. And the goal was just to get the text, but not these glossaries. But what our net did, it was also returning the interglossary lines as baselines, and therefore we got very bad results in the beginning. So what we did, we tried some kind of transfer learning. So we took our net, we just continued to train it, and we got better results, but we outperformed it just by 0.22% in total, but we were not 100% satisfied, so we retrained the whole stuff from scratch, and we were able to outperform it in all categories, and we were happy because then we can publish this stuff. Let's conclude. In contradiction to all the other methods that are proposed up to now that we're using LSTM networks, we came up with a completely different architecture. So we came up with the unit and this sliding window approach, which proved to deliver quite convincing results for simple structures, as we showed on the track A. On the track B is a little bit more complex, so there is more work needed in there, which we not go for because we are, as a company, we're not interested in historical documents. We just joined this competition because we wanted to have some kind of evaluation matrix for our software that we're currently developing. But from the scientific point of view, much work has to be done here. So either you should develop some kind of classification, a pixel-wise classification, where you can say for each pixel, okay, this pixel belongs to the foreground, this pixel belongs to the background, this pixel is a table pixel or an ornament or something like that. So in case you really want to improve your results on highly complex document, there is definitely some work to do in here. Yeah, I'm already finished. Yes, okay. So I'm open for questions and thank you for your attention.
What's the runtime on how large images on what hardware?
We have a dual Xeon workstation with a dual Titan setup, and for a 5 megapixel image, it's about 30 to 40 seconds. But the runtime is not linear to the input image size, of course. So there were even much bigger images in the data set where you even sometimes you wait 2 to 3 minutes. But runtime was not an issue at this competition. You just had to provide a text file with your baselines, and we didn't do any optimization up to runtime. Any other questions regarding the architecture or something? Okay, then just a reminder once again, you can download the slides and also our paper in case you're interested. And we would be great to hear if you find our paper useful, and in case you use it, please cite us. We need a good citation count. Okay, thank you very much.
So we are now done with all the presentations and with the official part, but please stay for a little bit longer and do some networking, talk a little bit more about document analysis or Singularity or whatever, have another beer, and feel free to stay a little bit longer for some networking. But thanks for coming, and I hope to see you all next month. And I hope I will get emails from all of you for doc proposals. Thank you. Martin? Thanks.